So one of my teammates is waiting in the room.
Yeah, just a second.
Okay, Sagars, you can start. We are live now.
Okay, great, Justina. So guys, can you share the screen now?
No, sir, still says disabled by host.
Yeah, guys, now it has been done. So
Good
hello
evening to
everyone, I
all the
welcome you all. Yeah, just a second, guys. So I welcome you all to the IRDC 2020 finals. And the first team which we have today is Team Rudra from SRM. And now they will be presenting their robot design. And guys, we have 15 minutes for that. And after we will move to the question and answer session. So you can start now.
We are Team Rudra, and this is our design for the IRDC 2022 finals. A short introduction about our team. We are the official Mars Rover team of SRM IST, and we are currently a member of a team of 35 members from departments including mechanical, computer science, electronics and communication, electrical and electronics, mechatronics, aerospace, and biotechnology. Our team has 5 domains. It's corporate, developers, mechanical, electrical, and life sciences. So Harsh will talk about the design of mechanical subsystem.
So the mechanical subsystem of the rover is divided into 5 parts: 6 degrees of freedom robotic arm manipulator, chassis, drive, wheels, and rocket glider. Let's start with the arm manipulator. So it's a 6 degrees of freedom manipulator used for picking and transferring samples from Martian terrain with the work envelope of sphere of radius 3.1 meters. The shoulder and elbow joints of the arm are powered through cycloidal drive of 1:96 gear reduction coupled with 10 Nm BLDC motor. The end of the arm is equipped with wrist joint of 3 degrees of freedom, yaw, pitch, roll for precise positioning of the end effector in any required orientation. It is powered by warm and firm filled gearbox coupled with stepper motors and uses. So an internal gear mechanism is used for roll mechanism of the end effector. Coming to the end effectors, we are using 4 different end effectors for different purposes, which are auger for collecting soil and ice samples and transferring them into biobox for analysis. Second, gripper for gripping and holding objects, can also be used for collecting bigger rock samples. Third, ice X for taking support and to get grip on the slippery icy terrain, like used by ice mountain hikers for getting grip on the ice. Fourth, Gulliver Mark IV apparatus, used for analyzing the environment prior to collecting samples, more on which will be further mentioned in the presentation. So, using these 4 end effectors on the single arm is made possible through the use of swappable joints, which eliminates the needs to place all the end effectors on the arm at the same time. The working mechanism of this swappable joint is already explained in the SCR documentation. Coming to the chassis of our system, the chassis is made of the bent box channel of titanium and aluminum alloy, which were made by channel bending. The chassis is designed in dome shape to avoid collection of any foreign snow or sand particles, which can increase the payload or also hinder the process of the rover. The chassis has compartment, which includes the analyzer box and arm, which are covered with sliding panels and can also be actuated whenever needed. So all the components of the rover are completely sealed whenever not in use. The electronics are further isolated inside the cell compartments with pressure conditioning. The 4 drive modules are planted in the separate opening compartments, and as they are designed to be heavy duty, work in harsh environments. RTG is kept at RTGS is powering the system of the rover, and it is kept at an isolated position from the center of the rover to avoid any imbalance in the temperature. Coming to the drive of the system, there are 4 identical drive modules with 4 degrees of freedom in each drive link. So, including 1 wheel drive degree of freedom. Each module consists of a 4-bar linkage engineered to keep the movement of the wheel in contact with the ground. The hip pitch movement is provided with 2 parallel links as actuation is provided at the 3 pivot, while the tubular linkage is provided at the bottom to give greater load bearing capability. Actuation of 3-roll pitch and steer has been achieved by pair of motor and cycloidal drive for compact and efficient use of power. All the motors of the drive module are completely covered in order to avoid any collection of dust or snow particles. Coming to the wheels of our system. Wheels were designed keeping in mind varied terrain conditions that rover will have to encounter. While maneuvering on soft snow, the wheels can be configured into multi-spoke arrangement that extends out from the wheel surface on demand. The extension range of the spoke is controlled by a set of rack-based linear actuator and a clutch mechanism, which pushes a spur gear inside, which meshes with the complementary gears in the spokes, gets opened first using curved spaced limiters, which has a line point of contact in the hub. The wheel's curvature is designed in order to remove any stuck matter which is left inside the wheel. Now, the wheels will be the part of the rover which will be coming into contact with the ice more constantly. So there are possibilities of contraction and expansion of the wheels of the rover. So we have given 2 degrees of freedom in the threads of the wheel so that they can expand and contract without giving failure to the mechanism of the wheels. Coming to the glider on Mars. The Mars rocket glider is a rocket-powered aerial glider vehicle intended to scan a broad area quickly and to examine areas of the Martian terrain inaccessible to rovers with higher resolution than satellites, as it is more nearer to the surface of the Mars. It is also intended to transport a small aerobiological payload. This is a multi-purpose vehicle that will launch from the rover and land at astronaut base station for reloading and maintenance to be used for future missions. The glider has pegged wingspan of 27 centimeters and deployed wingspan of 3.4 meters. The rocket glider is launched from the retractable launch pad connected underneath the rover's chassis. The rover's engine propels the glider up to 4 kilometers before starting to gliding. Now, Isita will be continuing with the bioscience part of the system.
The life science domain has established a biological analysis plan in an original, mission-oriented, and a scientifically feasible manner. The site of exploration is the southern polar plane of Mars, known as Planum Australe. More specifically, the soil ice boundary covering the latitude 74 to 77 degrees south. We chose the site of sample collection with the help of biosignatures. Here we go for phyllosilicates, cryptoendoliths, gold seeds, and fluvial patterns. We have a camera on board which would relay the feed to the base station and enable us to choose the potential sites. The samples will be collected using an auger. Next slide, please. The samples will be collected using an auger. The soil and ice samples. The soil samples will be undergoing further analysis in situ, while the ice samples will only be collected and stored for further analysis at the base station. Next slide. The gases that we will be aiming to find there are methane, ammonia, oxygen, carbon dioxide, and nitrous oxide. These gases would help us to find the atmospheric composition of the sites, compare it to the known Martian atmosphere, and also indicate metabolic activity. For the local weather characterization, we will be looking for parameters like temperature, pressure, radiation, humidity, wind speed, and direction. Next slide. These parameters would help us to forecast the future weather patterns and also determine the habitability potential of the site. The aerobiological investigation would include the presence of a PTFE, polytetrafluoroethylene filter, on the rover as well as the drone. The bioresols which will be collected onto the filter membrane will further be analyzed at the base station. For the in situ analysis of life detection, we will be using the EDX and the Gulliver Mark IV device. The Gulliver instrument will use the isotopes of nitrogen, oxygen, and hydrogen as radioactive substrates, which, if at all microbes are present in the soil, would metabolize these into radioactive substances that could be detected by the Gigamolar sensor also present in the same apparatus. The elemental analysis would be done using the EDX. We would try to look for elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, as these are the basic elements that form all complex biomolecules on Earth and also support carbon-based life. That's it from life science.
So coming to the electronic domain, the main objective of electronics was to connect all the peripherals and control the actuators and power the whole system. So due to the low temperature environment, every sensor has been carefully chosen. So, and since the mission time is 20 hours this time, an efficient power system has been implemented to keep the system operating all the time. Furthermore, the Mars orbiting satellites are being used for long range communication up to 50 kilometers from the base station. So coming to the onboard computer, our primary processing unit will be the NVIDIA Jetson AGX Xavier. It is a system master and will carry out the computation and the image processing tasks of the rover. The rover is equipped with 3 subsystems that will talk to Jetson to carry out other specific tasks. All the drive motors are motor drivers are connected to STM32F407, which will be acting under the Jetson. And all the sensors on board are hooked up to an Atmega 2560 SoC, and the drone on the board will run on a Beaglebone plaque to perform the aerial mission. Coming to the power system, we are using a plutonium dioxide fuel-based RTG as the main energy source. It will be providing a constant power of around 150 watts for the rover. We have used plutonium as a fuel because of its half-life period of around 87.7 years, which will ensure that the rover will be operational for many years across many missions. Also, lead telluride or thermoelectric couples are being used. So moving on to the sensors, we have several individual sensors which are used to figure out and analyze the different biosignatures. The biosensors are fed into the Atmega 2560 through analog pins and other GPIO pins, which will communicate with Jetson through the serial port. So talking about the drone, our rover consists of a new system which is designed to collect air samples and measure radiation levels from different altitudes for the aerobiology investigation. Coming to the communication part, currently there are 8 Mars orbiters which are active. So we'll be making use of one of these satellites which will be orbiting at a low altitude for communication. The altitude of the satellites are around 250 kilometers. So the rover will communicate with the orbiter, base station, and DSN through X-band radio waves. So we also have an onboard high gain antenna which can send a beam of information in a specific direction, and it is steerable, so that the antenna can move to point itself directly to the orbiter. So while the orbiter passes over the rover, data and instructions are transmitted back and forth between the rover and the base station. We are using satellites because there's no line of sight between the rover and the base station. So now we'll be moving on to the developers domain.
Our rover will use the F prime software stack. So what is the advantage of a F prime software stack? It is a purely C++ library. So it is extremely lightweight, and it turns out that when you compile the whole stack, it comes less than 10 kilobytes. So that's extremely efficient, power efficient in a very tightly integrated environment. And added advantage of F prime is, let's say you updated the configuration file and then it got compiled successfully, then it is guaranteed that your software stack will run. So that is guaranteed by F prime. F prime is already being it is developed and is being used by NASA, and it is the Ingenuity of the Mars 2020 currently uses the F prime software stack. The development is already the development, testing, and debugging is extremely easy in F prime. Our rover will be using the Z2 stereo camera for the depth data. Advantages of it is its robust design, and more importantly, the essential sensors that it has: IMUs, barometer, magnetometer, and the various temperature sensors that is already inbuilt in Z2 is crucial for our bioscience tasks. Next, I'll talk about the topology. So I already told you about the stereo cam, and the platform was described by the electronics. So we'll be using NVIDIA Xavier AGX. So we have, while using NVIDIA Xavier AGX, we have the capability of using both the Tensor and CUDA cores. So that will be extremely useful for the matrix calculations when the extended Kalman filter is being used. And F prime models will be simulated and fine-tuned for our use case. Let me tell more about the extended Kalman filter. We get the basic landmarks from the satellite data, and the data that we get from a stereo cam will be used to localize our rover in the icy terrains of Mars. So here we'll be using the EK filters to localize our rover in the terrain. By using EK filters, we can also reduce the drift and errors that accumulates over time due to the various IMUs and encoders present in our rover. It is traditionally said that EK is computationally expensive, but we have researched and found out that with correct tuning and when it is tested physically and optimized, it can turn out to be really useful and not that much computationally expensive. Lastly, I would like to tell you about the behavior tree that we have designed. So when you are exploring such a vast area and you have constrained mission time, you need to select specific areas for explorations, right? So the use of behavior tree is utmost here. So what behavior tree basically does is it compares the site present with the desired state that we already input to the rover. So if that site matches our desired value, the rover will go there and perform all the tasks. So this way, we won't be wasting time in areas which are not really suitable for all the life science tasks that we'll be doing. This is basically done using a best first search algorithm. And this will also make sure our rover uses the mission time more judiciously. That comes to an end of our design for the IRDC 2020, and we are open to questions from the jury members.
So guys, that was a good presentation. So now the judges.
So can I start? Is anyone else having?
Yeah, Pranav, you can start with your question.
Yep. Okay. So first of all, really, I really like the mechanical design and some really good job at that. I did, however, have some questions around any kind of research, considering that the whole goal about of IRDC was to kind of have not have too many limits on budget caps or execution, but actually design a rover that can work on Mars, right? So what is the amount of let's say in terms of simulation or in terms of analysis of, like, say for example, the clutches, what kind of approaches have you taken to validate the working of those systems? First thing, like, yeah, maybe we can go question by question. I have a few. So maybe first we can go ahead with the mechanical subsystem. What kind of approaches have you taken to validate the kinematics of your, let's say, your suspension or the clutch and the force required for all of that to work, right? So is there any kind of dynamic simulation that you guys have worked on?
Yes, sir. My name is Ayan. So while
Yeah.
working on the design of the wheel,
Mhm.
actually we have been working on a project of a reconfigurable wheel to climb
Okay.
staircase. So
Okay.
with the research of that, this type of mechanism has been used to climb over the staircase, because if you take any of the passive mechanism, so you either need to apply rocker body or anything to maintain your center of mass while traversing a stair. So we have applied that same research, and yeah, we have done the calculations, like whenever you see the design, like can you show the design? Uh, as you can see in the design, there are 6 spokes which are in a certain curve. So the curve comprises of the calculation that whenever the wheel is rotating on a surface, then at least 2 of the line contacts are always maintained in the ground. So let's say if you are having a dig hole where you need to traverse over, or wherever the rover gets stuck, or wherever the rover isn't getting enough traction to go. So the design of those curves are are made in such way that they get at least such line of contact so that it could come over that obstacle. So, and from the point of analysis, we have done some preliminary analysis in SolidWorks analysis, and about the clutch mechanism, we have just done the calculations, and we have followed the research which have already been done by the researchers. Yeah, that's all.
So what kind of clutch is this? Is it like some kind of a dog teeth kind of a thing, or is it a membrane-based asbestos? And what kind of a clutch is? What materials are you guys using on?
It's a completely mechanical clutch. It consists of a coil spring, and it is based upon a rack-based linear actuator. So what happens is, at a normal position, the spur gear inside it is always left out. So whenever the wheel is normally traversing, all the spokes are closed. And whenever we push that thing, the clutch powers it, and the spokes in the gears in the spokes meshes with the spur gear, and the power transmitting from the drive motor first turns and actuates the spokes, and after a certain limit they get stuck, and now the whole log system moves together. So like this is the basic principle. Using only one actuation, how can we attain this type of movement? So our basic approach is, if we go for a unidirectional movement, let's say as you are seeing here, if we push the spur gear inside and then actuate in anti-clockwise direction, first the spokes will turn up and then the whole wheel will turning up. So by this thing, we are achieving this.
Got it. But yeah, that looks good. So now coming to like the electronics part of things, right? So I remember reading in the report about the kind of hardware that you had chosen. Was there any specific reason as to why you guys didn't go for like more industrial hardware in terms of the electronics? Did you feel like what you guys were using was already good enough, or what was the reason? Like, say for example, I think I remember seeing that your motor driver was Cytron and things like that, right? So if it would be great if you can just probably elaborate on how did you go about component selection for your rover, and what were the parameters considered?
Okay, to begin with, the reason we considered most of the commercially available ones are because of its usability and working temperatures. We found it easier to integrate all the complex actuators. The number of actuators were quite few, so we wanted to integrate them all to control them in an order. So, which is why we went for the mostly usable motor drivers.
But did you consider the? I don't think I don't think even the report I remember reading about the approach for control systems, right? So how are you going about? You, like you said, you have like a lot of actuators. Correct me if I'm wrong, but I just didn't remember that in the report. If you, how are you going about the control system part of it? Is there any kind of RTOS implementation to make sure all these processes are happening parallelly? Or how are you making sure? Because again, the drawback with these motor drivers is the fact that you don't get the responsiveness that you want. If you want the motor to be actuated at like a particular nanosecond in time, you're not going to get that. And at like Martian environments or like at remote missions, you want that responsiveness, right? You want the rover to do what it has to do at the particular, not even millisecond. I'd go to say nanosecond, right? So was there any consideration on that front? Did you feel that okay, you didn't need to operate at that speeds? Or do you have like a plan for how the control system was going to work in terms of some state machines or something like that? That okay, at this state I need these actuators to be working. Is there any diagram of sorts that you guys have?
Yes, actually, as you mentioned, we did consider using RTOS for the operation, but then we mostly went for timed operations where we had to just perform particular missions at a time. So there was no need to actuate all the motors that you see on the screen at once. So at a given time, we were using only a few number of actuators. So controlling all of them simultaneously wasn't a requirement. Because we would choose all the waypoints and the operations. We would direct them from the base station. We would command them. We would code them. After which it would perform in a sequence of operations.
Okay, got it. So, okay, so yeah, then just feedback on that front. Maybe I just go back into the kind of outputs that you get from these drivers. In terms of, you'll have to have some kind of closed loop control, right? You'll have to get the feedback from your wheel encoders. And I also didn't remember what kind of wheels, what kind of motors are you guys using? Is it DC, BLDC, and what is the whole control algorithm? I mean, what is the kind of motor? Is it BLDC or DC for the drive?
For the drive, we'll be using DC gate.
DC gate motors. Okay, got it.
Yeah, for the arm, we'll have BLDC.
So then again, DC gate motors, there's like a very important reason why it's not very widely used in, let's say, like remote, like especially on rovers, right? The reason is like the brushes wear off over like a long period of time, which is why they go for like PSM motors or like BLDC motors, so that you don't have to deal with that. You can have machine life for like years together, right? So that's just like feedback probably for your next IRDC. Just I think your electronic subsystem, even in the report, was not very convincing on the reliability front and the precision and accuracy front, which is very important for like a remote mission. So that is one feedback that I had for that. And coming to like the software subsystem, I saw that you guys were using EKF, but I didn't see enough parameters for how are you getting odometry. Like I think I'm assuming you're only using the Z camera, right? How are you getting the odometry for your autonomy? What are your points for odometry for the autonomy?
Okay, so we have an onboard IMU, and also we'll be monitoring the wheel encoders. So in this way, there is a tendency for the wheel encoders to drift over distance, and there is a tendency for the onboard IMU to drift over time. So we fused these two data to get a more reliable odometry data.
Now that's the problem, right? Now in your wheel encoders, all your 4 wheels operate independently, right? As in like they have the potential to go up and down depending on your suspension or the rocks that you're climbing, which means any kind of rotation and direct data that you take is not going to give you accurate odometry. Like you might be climbing, let's say you just go over a rock. So one wheel you would have traversed more than the other wheels, right? Like if one wheel is climbing over the rock, in which case your odometry would be completely skewed. And your IMU is also, you're depending on the IMU for roll, pitch, and yaw, or only acceleration?
We'll be using IMU for both roll, pitch, yaw, and also the distance travel. Yeah, so the distance travel, right? So in that case, again, you'll face the same issue with when all of these are getting fused with EKF. You're not going to get like I don't think you guys will be getting the results that you want in terms of just using these as odometry. That's why I was wondering if you're using the Z camera or some kind of visual odometry to be able to get a more accurate. So what is the Z camera being used for? Yeah, correct. That's a really good question, sir. So the Z camera we chose primarily because last time we were using LiDARs, but this time the Z camera gives you a 3D spatial data, and that will establish some crucial landmarks which is nearby the rover, and the data that we feed to the rover beforehand, which is coming from the satellites orbiting the Mars, will have those landmarks. So major landmarks will be there on the rover itself. So by visually comparing the data received by the stereo cam, you can localize the rover accordingly. Like basically you have a local cost map.
So you'll be using some kind of you'll be using Visual SLAM also for
exactly
localization. Okay.
Correct, sir.
Well, yeah, guys, I think that's pretty much it. Just one very quick feedback is I just feel you guys like restricted yourself too much from building an actual rover for IRC or URC and IRDC. Like IRDC basically can go crazy and actually build an industrial grade product, right? And even with like the way localization and electronics, right? Like the way autonomy and electronics is approached, I feel like just go a little bit more deeper. That would be like my short feedback. That's it from my side, guys. Yeah, others can take over.
Okay.
Yeah, one
I have a
quick
question
from my side. Anurup,
please.
before we proceed. So as Pranav has mentioned, last time you guys got innovation award for your drive system. But this time when I go through a report, I hardly find 50 or 60 words in that. There are literally 4 lines, 5 lines there, and I hardly get any information from it. And there's the picture like from which I get some idea like what will it look like or something. So I'm curious to know like how your report making proceeds, because if I compare it with last time, the area where you scored maximum is the area where you are scoring minimum this time. Yeah, guys, anyone who want to answer this?
Yes, sir. Sir, can you please repeat your question?
What I'm saying is that last time you performed exceedingly well in drive system, and in fact you got an award, innovation award for that. But this time when I go through the report, I hardly find anything related to drive system. There are literally 4 lines there. When it comes to wheel, there are additional 4 lines. So the entire system, entire thing you have mentioned in those generic 7 to 8 lines. So as far as the report is concerned, we were not at all satisfied with that. Now after going through a presentation, we are more satisfactory compared to that, and we know something about that drive system wheels, but there was not enough in the report related to that part. And I'm surprised, especially because last time you performed exceedingly well in that. The report was quite good, and all the systems were properly mentioned and explained in your report. So I'm just asking what is the reason behind it and how do you proceed with your report making?
So as far as the report making concerned, there are major drawbacks which we have in the previous design of the drive system, although it was the best innovation that we can put into. So like we had taken inspiration from the old drive system and we have restructured it. Like previously, the major fault of that was there wasn't enough covering or measures taken to avoid the dust particles to go inside the mechanism. So this time we have taken special care of that. And although we have already mentioned the previous design, so we have already worked on to. But this time our major focus was
Sorry
on
to
the
interrupt you.
reconfigurable wheels. Yes, sir.
My question was not related to drive system. My question was, there is nothing related to drive system in the report. It's just 4 lines. By reading those 4 lines, I am unable to get the entire picture of that system. That's what I'm saying. So after your presentation, now it's clear to us, but earlier it was not clear to us. So how do you distribute your space in the report? You have 26 pages. Like how do you decide like which system should be more emphasized on?
Correct, sir. The content for mechanical subsystem was less. We came to know that also. We were actually on a time crunch, to be honest. We couldn't fill up the content within the time frame that you had given us. So we couldn't honestly complete the report fully there. So we thought we'll make up in this presentation as far as possible.
Presentation.
Yeah, because last time, as far as I know, you were quite satisfied with your mechanical part, and you were one of the best team. And you came for that also, like there was not huge margin. It was a very small, minute margin. And we thought if your other aspects improve, then that will also help you be there in the top 3. But yeah, this is one session from my side. Just distribute space strategically, especially the areas where
Even the
well
renders, for example, like the renders on the presentation were way better than the renders on the report. So this was like very convincing. That's why the mechanical system was like, yeah, what Sagar saying, yeah, that way makes sense.
Yeah, I think we need to finish anyway. So thank you for all the remarks and explanations. And we are waiting for another team. So good luck.
Yeah, just last question. If okay.
Can I ask a quick
last question? Yeah.
Sure. So in the report, you have mentioned that the site you have chosen, southern polar plains of Mars, that particular site has like minus 153 degrees Celsius. And at that temperature, I don't know of any organism that can thrive. So like around minus 20 degrees Celsius, most microbial metabolisms pause. So, what was the motivation behind choosing that site? And do you expect to find extant or living microbes there? Please answer quickly.
The site was actually already very clearly mentioned in the problem statement, and as we know that there was water present on Mars once upon a time. Right now it's barren, but it could be preserved in soil, and there is always possibility for. We know that the life exists in the Antarctic sheets, although not at the temperatures as low as on Mars. So we just decided to explore and look at the preserved life in the ice sheets there.
Okay, that's great. I don't think we have enough time, so let's proceed.
Thank you, guys. Thanks for the presentation. You may leave.
Thank you. You can leave now.
So guys, the next team which we have is Team Inferno from D to Delhi, and they have been participating since first edition of IRDC. It's their third edition. They were also there in the bonus rendered image task, where they have performed extremely well. So guys, are you ready? Okay, before you start, just let me remind you, you have 16 minutes to complete your presentation. Once you complete that, for the next 15 minutes, we will have the Q&A session. And during the presentation, only 4 of you can present. And later on, all 10 of you can take part in the Q&A session. So guys, you can start now.
So shall we begin?
Yes, you can start, but your voice is echoing. Yes, please check that.
All right, so a very warm evening to the respected judges present here. We are Team Inferno DTU, and we are for the final iteration, for the final round of International Rover Design Challenge 2022. We present our rover Aranyak here. We are from Delhi Technological University, a team of 28 members, and following waterfall topology, our team has been divided into 5 sub-departments, namely science, software, corporate, electrical, and mechanical, for efficient management of the team and its tasks. Now, presenting to you our rover Aranyak, representing our culture, our ethnicity, and the features and capabilities of the rover. We have named it Aranyak as it means the ones who can tread the terrains that are unreachable for common people. We have in the following slides, we would be dealing with the problem statements, namely how the rover would be traversing through difficult terrains, and how it would tackle with dust storms, low temperatures, how it would manage energy sources in such environments, the noise in the communication system, and how it would be collecting different samples for science-based tasks simultaneously.
The wheel developed for the rover has a self-operated mechanism which is majorly made of aluminum alloy. The main components of the wheel is the outer ring, the inner spike hub, and the spikes. The outer rim is made of aluminum. The inner spike hub is made of aluminum 70-75, and the spikes are made of titanium gold alloy. The spike mechanism the spike mechanism comprises of retractable spikes, the spiral hub, which is a hub for the wheel, and the spike actuator. There are two linear actuators. The length of the actuators decides how much the spike will go out and come in. The relative motion of the actuators provide relative motion to the spike with respect to the whole wheel. It also provides friction with the surface and the stability at times of storm. We have used the bar differential for the rover. It is located at the center or near the center of mass of the rover. It provides leveling for the body. It provides relative motion between the suspension. When one rocker goes up, the other rocker provides the opposite motion. It maximizes the contact with the ground and
Coming on to the suspension, we were intrigued by the design of Curiosity rover for designing of suspension because of its durability and distribution of weight. Now, the dual motor mechanism, the dual motor mechanism is infixed on the 6 wheels among the front and the rear wheels, which help them to move them in a synchronized manner together. The chassis, we have made a chassis which is in shape of a heptagon. It is a custom made base chassis, so that all the end effectors and all the different parts could fit in easily without any hassle.
This is an exploded view of the whole chassis, and as you can see, it is comprising of the robotic arm, the cam mast, and the connectors and the storage boxes for collecting the samples. Moving to the robotic arm, it is a 6DF robotic arm. It comprises of worm, spur, and rotatory actuators. It has a serviceability of 3 meters. It is equipped with switchable end effectors, which does not require any sort of human intervention. The shoulder and the elbow lengths of the robotic arm is made of carbon fiber for its strength. We have used gearboxes, which are made of insulated aluminum. It has interior aerogel layer and exterior gold plating for reflecting away the cold winters in the Martian atmosphere. These are the end effectors that we have used for the robotic arm. The first end effector that we have used is a drill. It is connected to the roll motor of the arm. It has 4 actuators for stability and minimizing vibration. It is made of 465 stainless steel coated with titanium nitride, which has high tensile strength and excellent notch tensile strength and high toughness. The next end effector that we have used is a scoop, which is used for carrying away the soft soil after the drill is used. The next end effector that we have used is the gripper. The gripper is made of aluminum 6061 because it provides flexibility to get a good grip, and it will be used for picking up the storage boxes and placing at the base station without any human intervention, and for picking up dry ice and rocks from the surface. The last end effector that we have used is a spectrometer, which is an X-ray chemical analyzer spectrometer, and spectrometer which creates fluorescence, which helps to detect extremophiles. This is the swapping mechanism used for the robotic arm. It contains 2 parts, the master plate and the tool plate. The master plate is connected to the arm and the tool plate is connected to the end effector. Once the master plate is lowered into the tool plate, the cylinder containing the taper is lowered and it gets locked with the tool plate. Similarly, at time when we have to unlock it, the tool plate also it has a taper which helps to push the ball back into the master plate when unlocking.
These are the storage boxes that will be picked through the gripper without any human intervention. Our rover Aranyak includes 6 storage boxes, 2 of which are used for storing rock, soil, and ice samples simultaneously, and also the XC2 for the XC2 analysis. The dome. We have used a dome. We have attached a retractable dome-like structure around the walls of the chassis to protect it from the dust storms, dust storms as well as the snowstorms. It covers both the surface of the chassis and the electrical subsystem during various anomalies. Coming on to the power source, the primary power source for the rover is the multi-mission radioisotopic thermal generator, also known as MMRTG. This source works via the Seebeck effect, also known as thermoelectric effect. The radioactive material we are using in this source is plutonium-238 because of its high half-life. The MMRTG generates heat by using MMRTG contains 4.8 kg of the plutonium dioxide, out of which only the 500 grams decay is in its 14-year life. The auxiliary power source. If the main power source fails, we are also equipped with an auxiliary power source. The rover contains the hydrogen nickel batteries for the backup power. The backup battery powers drives the motors, nav cams, and the antenna, so that the rover can move back to its original position if the power fails. There are 3 batteries on the rover, each of which has a capacity of 48,000 mAh.
Moving forward to the CPU. CPU is the main computing unit of our rover Aranyak is RAD 750 processor, and it uses 2 such entities where one serves as the main and other as the backup unit. This chip is used because its versatile ability to work in atmospheres with stray radiations and extreme temperatures, as it can withstand 1,000 grays of radiation and can operate in temperatures as extreme as minus 55 degrees Celsius to 70 degrees Celsius. Further, RAD 750 is based on PowerPC 750, and its packaging and lodging functions are completely compatible with the PowerPC 7XX family, which make it ideal for usage on the rover. And the microcontroller used in our rover is STM32F77500, and it is based on the ARM Cortex M7. It drives all the motors and sensors of the rover and contains 320 KB of RAM, 64 KB of flash, and 216 megahertz clock frequency, which fulfill all the requirements on the rover. And it takes command from the main computer and then signals the motor driver to provide the required current to the motors, so that the rover can sustain the movement efficiently and avoid jerks in the movement.
Now, after being aware about all the systems of a rover, what's important is to set up communication between the system and the base, which is provided 20 kilometers away. For that, we have located 2 antennas at the back of the rover. One is the ultra high frequency antenna and the other is the high gain antenna. Talking about the ultra high frequency antenna, it works at the frequency of 400 megahertz. Why? Because moving beyond this frequency, there is a loss of power, and moving beyond lower this frequency, we have a data loss. It is used to send the information from the rover to the orbital and then back to the base communication system. X-band high gain antenna. This receives commands and from all the omnidirection, it receives commands in an omnidirection, and it is capable of sending the beam of information in a single direction, so that the antenna can move, so that the rover can move to the base station itself. The benefits of having this is that the rover as a whole does not have to rotate to communicate. The vision systems. We use 6 hazard cameras, 2 in the front, 2 in the back, and the remaining on the sides to avoid the obstacles. 3 stereo cameras are used, 2 on the front and 1 on the arm, which helps us in the autonomous navigation and inverse kinematics. 1 camera is placed on the gripper that helps during the collection of the samples. As you can look in this chart.
Coming on to the thermal, as the temperature can reduce to as low as minus 140 degree, we have designed a thermal control system that couples all the hardware present which may malfunction during this temperature. This system uses gold, which reflects away the cold wind as well as the radiant energy on the Martian environment. Radioisotopes heater unit, also known as RHUs, provide the constant power of 1 watt without being a burden on the main power unit. Coming on to the software subsystem, the 2 CPUs on the rover run on the Linux operating system and the main software stack for the control communication, and all the other things are designed over the ROS operating system along with our custom-made ROS bags that will be used during the mission. The control and commands is being given through the ROS, and that is designed keeping the distributed computing in mind, which allows access to all the nodes running on the ROS master simultaneously at a single time.
Autonomous navigation is achieved with the help of cameras, GPRS, and thermal imaging. For that, we use atom mapping SLAM to localize the rover and build a 3D map. Our global path planners use Dijkstra's algorithm to find the shortest and most optimal path. The map is helps in path traversal. The inverse kinematics of the arm is an extended Jacobian technique which helps during the drilling of the rover. Its calculations are done on the CPU but not on the MCU. We use optimal encoders and for the orientations. When there is a malfunction, we switch to the backup CPU. There are different packages, and these packages have two nodes which help us to switch between and get to know about the new topics and nodes.
This is the chemical analyzer using X-ray diffraction. So to achieve different types of interference and basically to analyze the geographical as well as the historical aspect of the location, as well as to understand more about the poles, we use the mass lens imager to get observation to know about the instinct. The next is the Mars environment analyzer used to get basic environment variables like the UV radiation, temperature, pressure, and radiant levels.
The remote mineral analyzer is an advanced type of microscope which is used to study about the minerals, textures, and structures and get about the geological past of the landing location. The mineral composition detector is also a microscope, but it works on the basis of the vaporization of the rock and analyze the vapor. The next, which is the subsurface analyzer radar, it is a ground penetrating radar. It is also used for the same purposes.
Surface hydrogen detector is a modified version of NMR that infers the types of carbonic compounds present in the samples collected. And the X-ray chemical analyzer helps determine the chemical makeup of the substances to analyze the elemental composition of the samples that may be collected from the terrain of the Mars. Concluding, the universe is endless and so are the opportunities it offers to us. IRDC is a step further in the direction of conquering the terrains treaded by none. Thank you and have a wonderful time.
Okay, so thank you for your presentation. Actually, I think I can start with some questions, and I want to talk about your design. Because your design is really, really complicated. You have so many mechanisms, especially if it's about wheels, and we know that this is the weak spot for every Mars rover. So can you explain me why have you decided to do so complicated design of your rover?
So the basic idea behind the design is that we wanted that with the problem statement that we were provided with was that we will be traversing along the ice cap of South Pole at the ice cap of the Mars. So we, as a precaution, we designed the wheel with spikes so that even if we traverse through this ice, we can use the spikes for stability on the ice. Also, at times of storm, we have designed the spikes for getting stability.
Okay, so do you think that so many mechanisms will work, for example, in such low temperature? Because we are on the South Pole, so I am worried that it's actually not going to work there. So yeah, what if it happens?
For that we have used the whole thermal system. We will be planting RHUs at the wheels for especially close to the motors and the actuators, so that they can work properly, providing them the temperature that they require.
Okay, so what about the dust and the influence of dust for all mechanisms?
For dust, we have used there is a transparent plastic that has been implanted at the sides of the wheel, so that no dust gets into the wheel and the mechanism is not affected.
Okay, I'm not convinced that this is enough, but maybe enough from my side. I think that I will let other judges to tell you a few things. So,
yeah.
Okay. May I go first?
Yeah.
Okay, awesome. So first of all, like very nice presentation. You completed early as well. It's great. So I have questions related to the science aspect of your rover. So I see that like I read your report, and in that I see a list of very comprehensive instruments related to analytical chemistry. So I don't understand the motivation for using those instruments. What I see is a list of instruments and then the features, what can they detect. So what I would like to understand is I'll give you a situation and you have to tell me how your instruments will help detect that particular thing. So the situation is I have 2 packets of curd. Okay, curd have lactobacillus bacteria. So one of them I drop directly on your site, and the other packet I autoclave that packet, which is I'm killing all the bacteria inside, and then I am dropping it at another site. So tell me, how will your instruments detect the presence of life? And in this case, one is extinct life and one is extant life. So what instrument will detect it and how? I hope the question is clear.
Yeah.
Yeah, one small thing I would like to add to what Anurup is asking. So before we proceed to that question, just can you elaborate what are your top 3 objectives in the science task? Like in science mission, what are your top 3 objectives? What do you want to achieve there? And before achieving something, what do you want to do there? So if you can explain that.
Yeah, so the top 3 objectives of our science task are, first of all, we would be exploring the biological potential of the soil ice boundary at which our rover is landed. Then we are to go for the weathering analysis, like the rocks and the soil which are present in that area. We are doing the analysis of them using our microscopes. And thirdly, we would also be doing chemical analysis and basically the subsurface analysis of that area, like what is present underground in that area, and process the results.
Coming on to your question, Anurup, I think the question you asked about lactobacteria, I think the analogy is something which is similar, but I think the type of organisms we try to find on Mars is not something just like lactobacteria. It's more of extremophiles, right? So the mechanisms or the instruments which we use is basically in that direction to find extremophiles. But if you ask me that how are we going to find such organisms even on Earth with these instruments, so the answer is that we have X-ray spectrography, we have fluorescence, and all these things are capable of, capable of catching different wavelengths, right? So the basic approach towards the science missions were that we have to, if you want to find life anywhere, that's the part of astrobiology. There's elements like genophs, which are the basic of all elemental life which we found anywhere, right? So our basic approach was we have to find instrument who can detect which can detect these kind of elements on the subsurface of Mars, right? But also, as you said, lactobacteria, I think the subsurface analyzer and all X-ray spectrography are some things which can help us to find the carbolic elements present in curd. But also, the way we try to find extant life is by analyzing the geographical location, which means that when we say that we are going to radar or map subsurface area on the poles, it means that we want to analyze the history of that Martian area, which means that at any point of time, which we can infer that, okay, in past, there were conditions there which we can, conclude from that, okay, in those conditions, life could exist. So that's another way of finding extinct life. But we have also mechanisms about analyzing rock, which can also help us to find extinct life. So yeah, that's the approach. If I'm clear to you.
Thank you for the answer. I have some general feedback. That is, when you are looking or designing live detection tests, make sure you have the microorganisms on Earth in mind. What you said, like your instruments will be detecting certain wavelengths, you have to be specific about what biomolecules they are going to detect. And in the report, I also found a line which said the gas chromatograph determines if a molecule is created geologically or biologically. It doesn't make sense. How will your gas chromatograph detect unless you explain the context behind it? So make sure you keep these things in mind. And one correction that it's lactobacillus. It's a type of bacteria, not lactobacteria. But yeah,
Anurup,
all
I
the
think
best
we'll move to
for the
next question.
Yeah.
Because we'll be sending them the report later on. So Yeah, I think Hubert has one question, and Anmol and Pranav also. So guys, you can proceed.
Really nice presentation. I really like it. But I have the question to the report. You wrote that aluminum sheets of thickness ranging from 2 centimeters to 6 centimeters are used. And can you justify that? Can you tell us like why did you use 6 centimeters of aluminum in chassis? Because like overall you have the mass of the chassis is like 900 kilograms. So it stands for like most of the mass of the rover. Can you justify this choice?
Yeah, so it's actually like it's ranging from 2 centimeter to 6 centimeter of thickness, but the whole chassis is made of a honeycomb structure inside it. In the honeycomb structure, we have put aerogel for providing heat insulation. So it's not actually whole solid, there is honeycomb structure inside it.
And don't you think that 900 kilograms is too much? Because like for sure, like I saw that you made some analysis of the chases. Okay, it's good, but like still, like I think it's too much. You can use much more thinner aluminum sheets and even composites. So is there any justification why like such a big thickness of the aluminum you used?
So we went for the aluminum 70-75 for its high strength to mass ratio. So that is, we had that in mind that we need to constrain the weight, but and for that we use 70-75 aluminum 70-75. But like as I said, that we were trying to import the heat insulation was the main thing for us. So we wanted that as much as aerogel layer we can put inside. So for that we increase the thickness. Also, there is also heat sinks which are coming out from RTG, which is also inside the chassis for providing heat insulation, like for heating the whole chassis, and so all the components, the electronic system, and everything works properly.
Okay, so I don't have more questions, but as a feedback, I can tell you that all of the electronics in the chassis are heating a lot. So most of the time, there's the problem with getting rid of the heat, not how to heat the electronics. You can use the heat that electronics produce itself. And so from the construction point of view, there's no need for having a 6 centimeters of aluminum chassis. But
can I add
sure.
Can I add a point? Yeah. So it's not that the heat sinks are always there for providing heat. We have also put heat switches, paraffin heat switches. We have put in them so that whenever the heat is required, we can supply heat. Although we have that in mind that okay, there will be electronics and it will be providing heat, but at sometimes if the electronics are not like every time the electronics won't be working, and at that point of time, we like if the heat is required, we can bring heat into the chassis. For that reason, we had that.
Okay, I understand. Like, but still, from the construction point of view, you can make it much more smaller than you have as for now.
Yeah, I get it.
So thank you.
Thank
you. Yeah. So good presentation, guys. I really liked your thermal control system. But your report, like it's little bit conflicting between like your thermal control system and your electronics section. So in thermal control section, you're mentioned like you have given a nice diagram and everything, but in your and you're pointing out all the systems, but in electronics section, you have mentioned that there's a piping system. So could you please make that clear, like where that piping system is and how is it working? Because in thermal control system, it wasn't very clear. Like I think you had an opportunity there to explain that better.
I didn't get your question. Like basically the how the heat sinks have been placed inside the electronics box.
Yeah,
heat sinks are fine, but you're talking
Yes,
about
sir.
your electronic component section that you have a piping system which keeps all the components warm so that they don't fall below the operating temperature. Let's say a component has a operating temperature of -30, but in Mars it's -40. So you're saying that you're somehow maintaining that system, and you mentioned clearly that you're using piping system. So how is that working? Because heat sinks, you cannot rely on heat sinks for doing that, right?
So we are controlling the heat. It's not that the heaters will be coming out all the time. As I said, we will be using heat switches so that whenever the heat is required, we'll be using it.
No, okay, that is fine. That you have mentioned clearly in the thermal control system. But I'm talking about the piping system that you have talked about. It's there in your report under the electronic components, and you have.
Sir, along with that TCS, we are using the heat which is conducted by the radioactive reaction which is used in the MMRTG. For that, we have specified the ducts all over the chassis.
Okay, all over the chassis. So can you please bring out that TCS diagram that you had in your presentation? Just want to know the location and how that piping system is working.
Sure, sir. Just sharing this slide.
Yeah.
So this is the slide you were talking about?
Yeah.
So the thing is that, as explained in the previous slide, we have used a honeycomb structure that is filled with the aerogel. So beneath this system, we have laid a pipings because the best way to radiate the heat is through radiation. So like the heat that is the waste part of the MMRTG is radiated through these rods, which is beneath the honeycomb structure, so that the electrical system must remain warm during the cold times. So in the report, it's our mistake that we haven't put it clearly, but the rod system is just beneath the honeycomb structure, beneath which all the electrical system are lying.
Okay. Yeah. This TCS system is really good, but I think idea is very good, but you could have executed and shown it more properly. Apart from that, nice presentation, guys.
Thank you.
Okay, so I think that the time is over and we need to finish. So thank you. And you can leave the room now, and we are waiting for another team.
Thank you.
Thank you, ma'am. We would definitely keep in mind the valuable feedback given by all of you. Thank you so much.
So next team which we have is Team Anureshak from IIT Madras. And like Team Inferno, they have been participating since the first edition of IRDC. So guys, are you ready for the presentation? If you're ready, you can share the screen. Just let me remind you that we have 16 minutes to present, and after 15 minutes will be taken for the Q&A session. During the presentation time, maximum 4 of you can speak, and after that, all of you are allowed to answer a particular question.
Yes, you can please share your presentation.
So who is sharing the presentation? Please share. Guy, let you answer something.
A very good evening. I, on the behalf of Team Anveshak, extend our warm greetings to the panel. We are a team of 40 passionate students from IIT Madras who build our own remote operated full-terrain rover, complete with a robotic manipulator and science payload. Since our beginnings in 2016, we have been working at Center of Innovation, wherein we have spent countless days and nights building our rover and participating in various competitions on an international level through the years. Our team structure, the technical part of the team is divided into electronics and software module, mechanical module, and science module. We also include a business module. All the different modules work harmoniously to build the rover. We are glad to be a part of this distinctive design competition. So how does our rover traverse? Let's start the traversal system. A rocker bogie mechanism was chosen for traversal of the rover, which is a great substitute for spring suspension mechanism. This mechanism aids in distributing the load over the terrain. Steering mechanism consists of 4 electric motors, 2 in the front and 2 in the rear, housed within the rocker bogie mechanism, which drive the wheels. A bar differential is used to ensure lateral stability of the chassis. Wheels are designed to provide maximum traction, keeping in mind that rover might traverse loose soil, hard soil, or snowy or ice terrains. Grousers are designed to be radial to prevent anything getting stuck to the wheel. Sawtooth edges prevent slipping in both directions, traverse and forward. Spikes help increase the traction on icy surface. Motor casing enhouses the motor and provides protection to it. Ceramic ball bearings are used, keeping in mind the extreme temperatures. Wheel rim holds the tire and motor casing together. Wheel frame is designed to support the weight of the rover and is capable of bearing shocks. Coming to the manipulator part. This is a 5 degree of freedom, roll and pitch of shoulder, pitch of elbow, roll and pitch of wrist or end effector. This is useful in exploring and interacting with the terrain, that is sampling of soil. We have used a compound gear train for base rotation, double stage cyclodal gearbox for elbow and shoulder. We have also used hollow circular shafts made of carbon fiber for the links. A cyclodal gearbox provides high reduction ratios, compact space, and minimal backlash. The 2 cyclodal discs are required for getting the required reduction ratio and offset by 180 degrees to reduce eccentric mass vibrations. Because cyclodal gears are inherently backdrivable, electromagnetic power of brakes are used. Now, the end effector or the gripper, a 4-bar mechanism encapsulating a worm gear, is used for parallel gripping. This would be useful for maintenance and object retrieval missions. The pitch uses a spur gear train, while the roll uses 2 spur gears. The science payload, the drilling or the auger bed. The end effector consists of a small drilling assembly which includes the auger drill. This enables the soil collector plate at the bottom of the drill assembly to collect soil samples. The arm rotates and puts the sample in the experimental compartment in the chassis where the onboard testing can be done. It is controlled using a linear actuator and a motor.
Good evening, sir. So I'm here to speak about the electronic subsystem of Team Anveshak. So the components used, we are using Pololu motor drivers, SOC FPGA, STM Blue Pills, and Raspberry Pi Pico. The electronics design architecture. So first we have the power system, which has a battery pack, and the battery pack has the lithium batteries, and it is connected to the power distribution board. Next is the communication subsystem. We have an omnidirectional antenna, and we have a dual band setup for communication, a high frequency and a very low frequency. Coming to the control subsystem, we have a drive PCB, in which we have 6 motor drivers and 6 encoders for feedback to control the speed of the motors. And we have ARM PCB, where we use 6 motors and an MCP2551 IC for CAN communication, and incremental encoders for feedback to control the speed of the motors. Then we have the FPGA, which consists of IR camera, thermal cam, RP LiDAR, IMU, and microscope. Then the science PCB consists of sensors and motors, and system monitoring PCB. Working. In drive control, we have 3 STM boards, which each control 2 motors, the left and right motors. Then FPGA acts as the central processor, and it's in I2C communication with the wheel STMs. Optocouplers are used to communicate to transmit signals between isolated circuits, and are also used to prevent back EMF. Then we have the ARM control. In ARM control, we use CAN communication between the ARM PCBs using MCP2551 IC. Then we use silica aerogel to coat the components to prevent freezing of the components. Next is the power subsystem. In power subsystem, we are planned to use lithium polymer batteries. The reason for choosing lithium polymer batteries is because lead acid batteries have a low performance rate, and RTGs were a good option, but they will cause mechanical instability due to its heavy nature, and they are also very expensive. Then lithium polymers are lightweight, extremely safe, and have low discharge rates. Then we implement a battery management system to manage the electronics of a battery pack. It monitors battery parameters, generates error reports, predicts the runtime of the battery, and also manages the thermal temperature. Next is the charging methods for the batteries. First, we thought of implementing the solar panels, but solar panels are highly inefficient due to the following reason. The solar energy reaching the Planum Australia is only about 25% compared to that on the equator, that is 589 watts per square meter. Then Martian dust and dry ice falls constantly over the solar panels, which reduces the efficiency of the solar panels. So we have come up with another idea, which is harnessing energy from dry ice. We know that Martian solar south polar caps have enormous amount of dry ice, and the dry ice already exists close to its sublimation point. So we are going to implement lead and frost effect, where we are going to heat the dry ice about sublimation point so that we can get its vapors to run a dynamo to charge the batteries. Next is the geysers on Mars. This is one of the phenomena that occurs frequently in the southern polar caps of Mars. Martian geysers are sites of small gas and dust eruption that occur in the south polars of Mars. So the idea is we have to detect these. So we are going to use a piezoelectric transducer to measure the pressure and calculate the RMS velocity of these gases. When the high pressure gas flows through at speed of 160 km per hour or more, we can expect a geyser to erupt. Next is the communication subsystem. The major problems faced are electron precipitation, then powerful dry winds and extremely low temperature, accumulation of snow on the transmitters or receivers. So some of the feasible solution is to implement a temperature control monitoring system for analyzing and monitoring the surface temperature of the antenna, and using polyurethane foams for barriers. They generally act as insulators and cut the flow of cold and heat. Frequencies used. We use a dual band setup, that is 24 megahertz and a 24 kilohertz. When the high frequency mode, higher bandwidth, loses connection or faces any high attenuation, then low frequency mode is enabled, but it has a lower bandwidth. Communication mode. Our highly power efficient communication module is designed to operate at 14.4 kilobits per second data rate. So for the short range communication from 0 to 200 meter, we are going to use wireless access points. For high data transfer rate, we are going to use MIMO, multiple input, multiple output access points. For mid-range communication, that is from 0 to 7 kilometer, independent communication links are used for transmitting data and video. Then we have a video transmitter and a video receiver to transfer data. Next is the long range communication, that is from 0 to 30 kilometer, which consists of 2 military radio modems. These modems could transmit and receive 6 PAL images every second. Then talking about the communication architecture, as I said earlier, we are going to implement a dual band setup. First, we will try to establish connection with the base station on 24 kilohertz and 24 megahertz. If the 24 kilohertz is active, then we will try to communicate with the 24 megahertz. If it is not active, then we will listen for the commands in 24 kilohertz, save video, stream in memory, and we'll constantly try to establish connection in the 24 megahertz. If we have connection in the 24 megahertz, then we'll start listening from the base station and process the input commands.
Greetings. This is Shakti Vignesh from the Autonomous Subsystem of Team Anveshan. Looking at the autonomous subsystems objectives, our objective is to autonomously navigate through the rough terrains of Planum Australis, avoiding the obstacles while simultaneously generating a three-dimensional map of the regions traversed. We achieve this with the help of three submodules. First, perception, then path planning, and the control module. Looking into the perception module, this takes care of generating the three-dimensional map of the region. We achieve this by applying a visual SLAM algorithm on the LiDAR and the stereocam data, that is received. Since the classic SLAM algorithms fail in sparse regions, given the fact that we don't have enough features to base our map on, so we use a visual SLAM algorithms based on the data. We use the RTAB map ROS package for this matter. As far as positioning is concerned, we use wheel encoders to measure the positions. However, the problem arises due to the fact that there could be slipping on the IC regions of Planum Australis. Thus, we use visual odometry since the vibrations in such places would be very low. We also use extended Kalman filters on the data received to minimize the overall errors. Looking into the path planning module, our objective is to make sure that the rover safely autonomously navigates itself while mapping the entire region. Thus, the optimization problem is to come up with the shortest route traveled, whereas maximizing the area that is mapped. We have customly designed an algorithm for this matter. We use something called as the approximated shortest watchman route problem algorithm, whose entire problem statement is to visually surveil a given area in one given path. But the problem arises due to the fact that there could be obstacles in the given region and we might not be able to traverse to those regions. So we pre-compute the path based on the satellite data we have on Planum Australis and load it onto the rover. However, there arises also another problem. We don't know if a given region is traversable until we go there, given that there might be some temporary changes occurring on those regions. There we use a frontier and A-star algorithm combination to navigate out of the ASWT path and also successfully dodge the dangerous part and also navigate back to the original ASWT path with lateral controllers such as Stanley controllers. So this optimization will be achieved by our algorithm given the 20-hour time frame. Now, looking at the heating subsystem of the team, there arises a problem that since we will be traveling in the Planum Australis part where the temperatures go as low as minus 153 centigrade, we have to have an active heating system for the rover to not fail in such situations. We have two methods of heating the rover. One, passively heating the rover by preventing the heat escape. For this, we use something called as aerogels, which we have discussed earlier. The silica aerogels, given their excellently low density, can be used to prevent heat escape while not mechanically affecting the rover. We also use gold paint to prevent heat escape via radiative transfer. Now, to actively heat the rover, we use something called as RHUs or radioisotope heater units, which produce heat through the decay of Pu-238. Also, given that we might be under very severe conditions. We also won't stay away from using active electrical heating if at all the conditions are severe.
Now I'll be briefly taking you through the science module. So what we basically do is we bring about a hypothesis, we further investigate using the various data collected, and we analyze using the soil samples, and we conclude on the same. Now the various sensors used to the same are the GRU multi-channel gas sensors, the GRU oxygen and carbon dioxide sensors, various temperature, humidity, altitude, pressure sensors, and also a sensor to measure the luminosity of ionizing radiations, an integrated soil sensor capable of analyzing various soil parameters like the pH, electrical conductivity, moisture content, etc. Now, I'll briefly take you through the southern Martian ice caps. The area of interest that is Planum Australe is the southern polar plain on Mars, and it has an elevation of around 6 kilometers above the Martian sea level, and it is partially covered by a 3 kilometer thick permanent polar ice cap. Now, compared to the northern polar ice cap, deserts have a higher concentration of carbon dioxide ice and frozen water. The layers are more thicker, more terraced, and have an irregular, heavily cratered terrain underneath. Now, the atmospheric conditions specific to Planum Australe. One is the condensation and sublimation flow. Carbon dioxide gets constantly condensed in winter, and it sublimates during the spring season. And this causes strong plate-wide atmospheric circulation, which is termed as condensation flow. Then strong winds. The Hellas impact basin steers high and low pressure wind waves in the atmosphere, and this causes the formation of canyons and carbon dioxide snow to fall more heavily on one side of the pole. Frost and large cirrus clouds. The large volumes of dust and water vapor transported through the condensation flow get formed as the frost and large cirrus clouds, and they form spiral troughs due to Coriolis force effect. And spring jets are also very common in this region, and due to the pressure buildup, they will eject at a speed of around 150 kilometers per hour, forming spider-like patterns. Now, various paleohydrological
your time is over, so you need to finish your presentations, and we need to move to the Q&A session.
Sorry, I think she has gotten disconnected. Please hold on a minute.
Okay, team, can we start with the Q&A session?
Right, I think we can start with the Q&A session.
Should I ask a question?
Yes, sir, please.
Okay. So, like first is I want to know about your live detection payload. That is, you're trying to use some very basic rudimentary tests, right? So I want to know the reason why you chose these tests, because when you are dealing with liquids on Mars, there is a chance of spillage, but also you have to spend a lot of energy on heating and keeping them in the liquid state. So yeah, I'm curious about that.
Hello.
I can't hear you. I think
I will
there
continue
is.
with the question.
Okay.
So, in addition to the basic test that we have proposed for the reducing sugars, proteins, lipids, etc., we also have certain terrain-specific tests as well as instruments specific to instruments catering to the various needs as well. UV spectrometer, UV instrument, and PCR instrument as well on board. and the to the high
You have a question? Because I have actually.
Yeah, so can I go with my question? Does anyone else have a question?
Yes, you can go and I can be after you.
Sure. So yes, so I saw that you guys are using lithium polymer batteries. What is the strategy for dealing with yeah, am I audible?
Yes, you are.
Yeah, okay. So I saw that you guys are using lithium polymer batteries. What is the strategy for dealing with them, considering the fact that they have a particular number of charge and discharge cycle, and you're sending this for the remote mission, right? How are you dealing with that uncertainty, and also generally the whole temperature controlling and the you know, they are prone to a lot of hazard. I mean, creating a lot of hazard. So how are you? What is the strategy for dealing with that?
Yes, sir. So the reason we have planned to have lithium polymer batteries is because they are cost effective and easy to install. And considering the weather conditions, yeah, in Martian southern polar caps, it is minus 150 degrees C. So we have planned to use RHU, that is radioisotope heating units, to heat the battery and keep it in the temperature to operate. And considering the discharge rates, as I said earlier, we are using the Leidenfrost effect to charge the batteries continuously.
Okay.
So that we don't, it actually ensures that we have a proper 20 hours long run.
Got it. Okay.
Okay, so I have a question. So I think your rover design is probably great for IRDC, but I don't see how you adjusted your design for Mars conditions. So can you please explain me more how it is going to survive on Mars?
Ma'am, like we have planned to actually heat the surface of Martian southern polar caps. So how are we going to heat is like we are going to implement RHU in the wheels. So that will be on the wheels, and
I can hear you.
Ma'am, could you please repeat the question on whether the emphasis is on the general mechanical module of the team
About
or
the mechanical and electronic subsystems and your design of the rover, because I have some doubts if it's good for actually Martian conditions. So if you can explain me how you include this into your design.
as far as heating is concerned, so we have planned to install the RHU inside the electronics box in the chassis actually. And we are going to heat the surface of the Martian southern polar caps by heating the wheels and capturing the vapors of dry ice, so that we can implement the Leidenfrost effect to charge the batteries. And yeah, so the RHU is going to make most of it. So it's going to heat the complete chassis and the rover, so that the rover can be driven in worse conditions also, even at those temperatures.
Okay, and what about radiation and what about dust?
Yeah, so dust is gonna actually interfere the communication subsystem. So we have already planned to have polyurethane foam boards which act as insulators in those conditions.
Okay, and what about radiation?
Sorry, ma'am, I didn't hear you.
Yeah, I just wanted to ask how you want to prevent your rover subsystems if it's about the radiation on Mars.
Can somebody please take that question? Or if you're speaking, you are mute.
So the question wasn't audible actually.
Okay. So she is asking about the radiation. So what is your idea or your plan to tackle radiation for your components?
So in general, if at all the radiation is EM waves, and we are anyway going to apply gold paint on the rover for heat purposes. So won't that in itself act as a Faraday shield for the most part? Given that we are not going to be applying completely gold cheese and we'll be applying some kind of conductor metal on top of it. So using a fairly simple Faraday shield would, in that case, would suffice.
Okay, so before we move to the other questions, I have a quick one. So you have mentioned the Coriolis force in your science module. In fact, we have dedicated around 2.5 pages in your report to the atmospheric conditions of that region. So I just want to know what is this phenomena of Coriolis force and compare both the forces, like the Coriolis force on Earth with the Coriolis force on Mars. How are they same? How are they different?
Coriolis force is like that act on due to the radiation of the Mars, and this is due to difference between Mars axis and Earth axis. It's not much similar as Earth, so we can expect the Coriolis effect according to the Mars tilt axis, and it is most appearing south polar elsewhere.
Also, the Coriolis effect on Mars is actually going less than that on Earth because the Mars has a smaller radius when compared to that of Earth. And also, the angular velocity of rotation of Mars is much lower when compared to that of the Earth.
Okay.
Okay, I have another question about the sublimation heat engine. And you said that you will heat dry ice under the rover during the traversing the pole. So did you analyze what will happen, or maybe maybe you have some backup for that, but what will happen if you will be in the place that you don't have like sufficient dry ice under the rover? What will happen then?
So when we researched about the Martian southern polar caps, specifically Planum Austral, we got to know that it is abundant of dry ice. So there are a lot of dry ice. Even though the rover goes to a place where we don't have dry ice, we can use the charge that is already got from the dry ice to run the rover.
Okay.
So guys, is there anyone left with the question, or shall we wind up?
Yeah, I don't have a question, just a feedback before we wind up. Your report was very good, guys, but I think you should have worked a little more on your presentation. Yeah, like a lot of the part of your report you have explained very well, but some places as Justina just asked some of those questions and related to electronic shielding and how you are planning on properly saving that, you should have probably put some more analysis in that. So yeah, all the best. Thank you.
Yes, thank you, sir.
It was good to have you guys. we hope to see you again. And just a final thing, please be on time. Your report also, your resume also, everything is going late. By years. Till last year, I don't know what was the culture in the team, but things were on time. But this year, please try to rectify those things because you simply lose points. And as it is, we don't want to cut points for any of the teams, but that is how the marking scheme is. And we are in no condition to not cut the points. So this time your report was late. That did hamper your chances a lot. So please, from next time onwards, be on time, especially when submissions are. So good luck, guys.
Okay, so thank you. You can leave the Zoom meeting right now, and
Yes,
we
sir,
are waiting
we'll make sure to be on time.
Okay, so thank you. You can leave the meeting right now. It was nice to hear you, and we are waiting for another team. So.
So the next team which we have is IoT Mars Rover, a team from IoT University, Bangladesh. And they have been around for quite a time now. I met them for the first time in 2019 IRC. That year they came third. So welcome, guys. And before we proceed to the presentation, let me remind you, you have 16 minutes to complete your presentation. And that will be followed by a Q&A session for next 15 minutes. During the presentation, maximum 4 of you can present. After that, all 10 of you can take part in the Q&A session. So guys, when you're ready, you can start. You can share your presentation now.
Can I start now?
Yes, you can start.
Hello everyone, I am Tanvir Hossain Rishad and with me are Farhan Shahriar and Minhajuddin Ahmad on behalf of Team IoT Mars Rover, here to briefly showcase you the journey of the manifestation of our rover. IoT Mars Rover is a team possessing the most brilliant minds from Islamic University of Technology, Bangladesh. We currently have 72 enthusiastic team members who worked hard to make this rover possible. These brilliant and young minds enhance their skills under 5 different subsystems: robotic arm, drive and suspension, mini rover, science unit, power and communication, with our team lead Sefer Abdulbari guiding them. IoT Mars Rover began its journey by completing the European Rover Challenge (ERC) for the first time in 2015, finishing in the top 16 in the world and second in Asia. IoT Mars Rover aims to be the role model for the young minds of our country to encourage them to join the promising and growing sector of planetary robotics. This team believes that through teamwork and perseverance, it is possible to exceed their expectation and attain success. Moving on to the goals. Participating and winning in competition, fostering leadership, communication, and presentation skills, developing and sharing technical skills related to important fields of engineering, connecting with an international community of rover enthusiasts. Here is a rendered image of the rover that we actually had in mind. If you notice closely, our rover has now has a younger brother somewhere in India, which we will talk about in depth later. Our subsystems include, as we have said before, arm, drive and suspension, mini rover, science, and power and communication system. Now I'm moving on to the arm section. Arm is a very important and crucial element of the rover. A robotic arm needs to be precise and capable of performing various tasks. With this arm has been designed, it can provide up to 6 degrees of freedom for completing any of the critical tasks. Manipulators such as gripper are adjustable with the arm to reconfigure if needed. While designing the robustness and the precise capabilities that has been considered, to keep it lightweight, finite element analysis has been performed and extra materials has been removed. Linear actuators has been used to provide better control and keep its vibration minimal, and to provide a backlash-free motion. In our rover, we have introduced external expanding centrifugal acting vanes to deal with ice terrains. We have mounted 6 pivoting vanes on the sides of the wheel. The angles of the vanes can be adjusted for the best possible traction by changing the position of the central hub. On ice, adjusting the vanes so that those underneath hook into the surface will pull out the rover forward. And in the soft snow, the rover would be able to compact the snow by adjusting the vanes to lie flat or use them as paddles to move the wheel. The vanes also can be adjusted to allow the rover to dig through the wall of snow and clear a path. Before designing, some criteria was set. Initially, 3 or 4 types of suspension were selected. Then, based on the criteria and applying a weighted method, the outstanding was chosen. And the chosen one was innovative 4-bar mechanism, accompanied by a spring damper suspension system has been selected for the design. It's a new type of suspension system which ensures to provide a more smooth and risk-free traverse of the rover. It was selected based on the following criteria: lightweight, initial low cost for manufacturing, improved road safety for the rover, a higher load carrying capacity. The suspension system operates in linear up and down motion while dealing with the uneven surface of the road, so the chamber remains unchanged, keeping the vibration minimal as possible. In a rover, as the team brainstormed what are the unique features the rover can be equipped with, we pondered with the question: what happens when the rover becomes incapable of reaching the remote places or the places difficult for navigation? The answer to that question was WASP, Wireless Area Spectating Project, an autonomous mini rover that can be deployed from the main rover body for collecting data and visuals from remote places where the main rover can't reach. WASP can also analyze the ice surface and water layers on the Martian surface with the help of rim-fact sensors, and can determine which terrain of the icy layer is safe to traverse for the rover. WASP is equipped with thermocam for thermal imaging, NavCam for taking wide-angle photographs, and high-powered carbon dioxide laser to melt the ice. The WASP was designed symmetric so that even when it's flipped, it can continue its usual navigation. The wheels of the WASP are vane-shaped and reconfigurable to traverse better on ice. The required functional period of the rover had to be at least 20 hours, which is why we opted for 2 different power sources. And as for ensuring seamless communication between the rover and the base station, we opted for 2 different antennas. Our power sources include 2 sources, which is primary power source and secondary power source. For the primary power source, we decided to go with MMRTG. MMRTG is essentially a nuclear battery which ensures uninterrupted power supply for 20 hours. It works by converting heat from the natural decay of the radioisotope materials into electricity. RTGs consist of 2 major elements. One is a heat source that actually contains the radioisotope fuel, and another one is solid-state thermocouple that converts the plutonium's decay heat energy to electricity. Perovskite solar cells. For the secondary power source, we use perovskite solar cells, which are made from synthetic material that has been modeled on the special crystal structure of a mineral called perovskite. This structure actually absorbs the sunlight in a different, more effective way than silicon cells. Recent study has shown that architectural structure enabled the perovskite solar cells to have 24% efficiency more, while retaining 87% of its original output capability after 2,400 hours of operation. That's a lot. For the communication, we went through 2 different antennas. The first one is high gain antenna, HGA. The high gain antenna is actually used for long distance communication. The best feature of HGA is that it can send signals without the antenna phasing on any particular direction. HGA uses radio signals that can cover distance up to at least 3 kilometers. And UHF, ultra high frequency antenna, will be used for close range communication due to its faster signal transmission. UHF sends and receives data at a given time. They can transmit up to 2 megabits per second.
For the science struts, the gripper of the arm will assist in the collection of the samples. The customized shovel gripper will collect the Martian samples, and it will be transported to the storage for the base station analysis and to the science box for onboard analysis. The science box. With the help of the onboard chemicals, we will test the protein, carbohydrate, and lipid profiles of the collected samples. The color change mechanism will be detected by in-house design of the science box, and it will identify the microbial existence in the sample. The rock and pinion mechanism will assist in pouring the chemicals to the desired test tubes. There is a two-layer sieve mechanism in our design sieve where the non-uniform particles will be filtered into rock and porous particles with the help of the upper sieve, and the lower sieve further filters into the fine particles which will be collected in the bottom collector, and the wasp will travel into the destination designed and melt the ice with the help of the carbon dioxide laser. The onboard suction pipe from the arm will collect both the water droplets and the vapor water particles simultaneously. The STPC TOU microscope will determine the mineralogical composition of the rock. The collected data will later be analyzed with the help of our database of the compositions. The pixel will determine the fine scale elements and composition of the Martian surface materials. Then, planetary bodies with and without thin atmosphere produces proper emission of neutrons and gamma rays from the substances. Dan will mainly produce the data of the hydrogen distribution profile and along with the rover path, which will assist to characterize the soil composition of the Mars surface. The MEDA. MEDA or Mars Environmental Dynamics Analyzer helps to analyze the temperature, humidity, amount, and size of the dust particles. MEDA consists of 6 core elements. The atmospheric temperature sensor measures the atmospheric temperature with the dedicated thermocouple. The humidity sensor measures the relative humidity and contains filler protection to protect from dust. The radiation sensor helps in the radiation is measured through the photodiodes of radiation and dust sensor placed on the rover deck. Mastcom Z is used for the dust deposition. Pressure sensor contains a tube with a small opening to the atmosphere. A HEPA filter protects the tube from the dust. Thermal infrared sensor contains 5 thermopiles, which is used to measure the net infrared thermal radiation near the surface of Mars. And lastly, the MEDA wind sensor is a combination of 6 boards per boom, which serves to determine the wind speed as well as the pitch.
Autonomous navigation system. The Mars rover can move autonomously from one point to another point given a destination. Much of the operator's workload is reduced by the autonomous capability of the rover. This is analogous to what we see in today's passenger aircrafts, for example. The autopilot system enables the pilot to focus solely on the critical tasks and the monitoring duties, while the autopilot system takes care of the nitty-gritty of the navigation. So this is analogous to what we want to accomplish for the Mars rover operator. The stereo camera used in the design can provide RGBD image of the surroundings. The D in the RGBD stands for depth. Every pixel has depth information associated with it. This allows the rover to build a point cloud of the environment and have 3D perception of the world around it. Data from the cameras along with onboard IMUs and wheel odometry allows the rover to run a sensor fusion algorithm for more robust probabilistic localization algorithms. This is important because all the sensor data are inherently erroneous. We cannot rely simply on wheel encoders or any particular sensor for our localization. That's why the sensor fusion algorithms is used, because no matter how much sensor image signal conditioning we perform, there will be still some errors. Then a simultaneous localization and mapping algorithm is used to do the localization and mapping part of the autonomous system. The path planning algorithm uses the map to generate lowest cost path for the rover to follow. This takes obstacles like rock, slope of the terrain into account. The algorithm tries to find an optimal path which is short in distance as well as in energy consumption while avoiding obstacles. Due to the specific nature of some parts of the terrain, the operator can optionally deploy the mini rover to traverse and explore the terrain first, and then compute the map for the mother rover to follow. A closed-loop control system is used for the motors and actuators to ensure that the rover is following the commands generated by the autonomous navigation system accordingly. Now the conclusion part, I want to hand over the slide to Rishad. Rishad, you are mute.
Sorry. Team IoT Mars Rover is the culmination of the hard work of all the enthusiastic minds devoting their time in order to build something truly remarkable out of sheer passion. Throughout the time, the team has been successful to mold the young engineers into problem solvers to prepare them for the futures that lie ahead, which is why Team IoT Mars Rover is the perfect hub for practicing technicality and a place for turning dreams into reality. Thank you.
Thank you very much for a very interesting presentation. May I have a question, Sagar?
Yeah, please proceed.
Yeah, I really like that you have two power source, and it was interesting to see a pair of skid solar panels. So can you explain us why have you chosen this solution?
Hello, my name is Asif Iqbal Turjo. I'm part of IoT Mars Rover team. So we are using perovskite instead of the normal PV cells because recent studies shows that the perovskite has better efficiency. And talking about the structure, the perovskite we can bend the perovskite, so we can use anywhere in the rover. We don't have to think of the storage or the capacity we have in the rover. So that's a big goal for us. And also talking about the efficiency, the perovskite has 25% more efficiency, and while retaining 87% of its output capability after many hours of operation. So that's why we chose perovskite over the regular PV cells.
Okay, thank you. I really like this idea. I think it's not like they have better efficiency, but they don't lose so much efficiency comparing to other panel cells. So I think this is a good choice, and that's the only remarks from my side. I think that the other judges can add something.
Yep. Can I go next, or does anyone else? Yeah, Pranav, you can proceed.
Yeah. So one thing is all your components, right, pretty much seem to be very exposed, like your actuators and especially your actuators. So how are you? What is the plan for dealing with that when you consider dust, thermal fluctuations, electromagnetic radiation? How are you dealing with that? Because I didn't see you guys talk about all that. Yeah. Hello. Yeah.
Guys, if you are speaking, you might be on mute.
Yep.
Hello. Hello.
Yeah.
Am I audible?
Yep.
The electrical components are well insulated, so and the weatherproof boxes are used to for the intricate components, and so this is our preparation. This was our preparation.
No, but what about your actuators? You have your linear actuators, you have your drive motors, right? So what about those? How are you protecting them? So these motors and actuators are also running on DC and all of that, right? So how are you protecting all of those things from minus 40, 150 degrees Celsius and all of that? Yeah.
The electrical box inside the rover body is
not the electrical box, the actuators on the arm, the drive motors, all of them are pretty exposed, right?
Yeah.
Yeah. So is there any plan to protect that? Is there any strategy in place, or you guys didn't consider that?
We particularly didn't implement any solution to remove the dust or anything, but let me share with you something that when we were researching, we found that there were some dust storms in which NASA thought that it will be a problem if the dust gathers over the components of the body, for example, like motor boxes and the solar panels, because it will reduce efficiency and create wears and tears in the motors. But what was found that sometimes dust storms go over the Mars rover, and it is very common. And it was found that sometimes these dust storms can actually remove the dust from the body.
Got it. But what about the what about the material with which those actuators are made? Like they're either using aluminum or steel, right? And these tend to change properties at lower temperatures. So I'm guessing the actuators you're using are normal electric actuators which have aluminum bodies and all that, right? So I think then probably next time just give that a little bit more thought. Yeah.
Yeah. Thank you for your feedback.
And the other thing which I want to point out, I really like the presentation. It's one of the best. The color scheme, animation, photos, everything is appropriate. But when I look at your report, it looks like that some other team has submitted that report. So there is no similarity between the both. There you have only utilized 20 pages, and that is not as good as your presentation. So what was the reason? Did you have less time, or were you unable to plan it properly? So what was the major cause for that?
For some part, we chose the options to be open. For example, we didn't mention, for example, when it comes to microcontroller, we didn't mention any particular microcontroller in the market. Because if it is a commercial product in the market, there is very limitations about cost and everything. They consider the price point and everything. So we are open to custom solutions that are developed in the research labs. So we didn't want to limit ourselves in particular model of microcontroller, particular model of the motor, particular model of motor driver. And yes, you were right about the time. We had our final exam, so there has been some issues with that time management.
Okay, that's fair enough.
Yeah, so I have just one question. So you are using this special kind of solar panels, right? And you have mentioned in your report and in your presentation that they are quite efficient. But for a mission of like 20 hours, even if it is quite efficient, do you think that it will continuously work since the mission is at the poles and the sunlight there would be marginally low as compared to, let's say, it would have been at the equator. So why did you discard the ideas of other battery sources and choose this? And what sort of parameters did you use while researching for this aspect of your work?
So mainly the 20-hour mark can be well served by the MMRTG, but we chose another one as a secondary option. So the solar panel is not our primary power source. It will charge the batteries as much as it can, because the sunlight is not guaranteed. So this is optional, like redundancy option. And about the so you have low sunlight, right? So you have to absorb as much as you can. So the perovskite solar cells are proven to have more absorption and can put burst of power even from low radiation. It can trap the lights. There are some photonic studies that shows that the particular arrangement of the atoms can be more efficiently used to capture actually absorb the sunlight. So how little we have, we want to absorb as much as we can, which cannot be accomplished by traditional crystalline silicon solar cells.
And what do you think? Like, can you perform the mission 20 hours at stretch, or would you need time continuously to recharge your solar cells?
The calculation was to continue for 24 hours straight. There won't be any delay.
Thank you. That's all from myself.
Thank you, judges.
Do you have any question?
So should we leave the meeting?
Yeah, I think that's it. So thank you very much, guys, for your presentation.
Thank you so much.
It was great to have you. Good luck.
Thank you for the feedbacks.
Thank you.
Sagar, so last few words, we can finish.
Yeah.
So thank you all for participating and watching us on YouTube. See you tomorrow on the second day, and we have a few teams as well. So be sure to be with us tomorrow, the same time, the same link. So see you.